came out with the guy with the camera, and I gave him an action shot to start, and it was very confusing for the rest of the thing. So for anyone who's just come on with the video, I was just giving you an action shot to get you started off by confusion to find out what we were talking about before class started today. What I want to do is I want to pick up and I want to finish very quickly what we were talking about with self-consolidating concrete and jump ahead to talk a little bit about curing. I will make a minor note. Those of you who are trying to get the last part of the second problem on homework, you will not get the exact answer in the back of the book, because when they solved it in the book, they actually used the finest modulus, not the specific gravity. So if you spend 17 hours trying to figure out how to get that exact number, you won't get it. You'll be off by about 10 or 12 pounds. But I wouldn't worry on that last part about getting the exact answer. It's really more the process. So when I left class, I showed you one of my fanciest simulations that I think I've ever done. I was able to take this picture of the L-box, and I was able to animate it in a very, very exciting fashion. The basic idea here is that we would have concrete. If you'll remember, we were talking about self-consolidating concrete, and we want to make sure that the concrete is going to be able to flow under its own weight. The ultimate goal of the industry is to be able to have a concrete truck show up on site, back up to the forms, fill up the forms, not necessarily have to worry about anyone actually being there to test the concrete or place the concrete, because there's a huge savings in doing that, and it means that the concrete can be placed at any time in theory. So I don't think we'll ever get to the point where no one will ever be out on site, but you can really minimize the number of people that are out there in the workforce. The basic idea here is this concrete is going to be placed into this the vertical portion of this L-box, and there's originally going to be a sliding door, and that door is down. I've shown this door here with the red being in the down position. In front of that door, it looks like the concrete's being kept in jail because there are a few rebar going up and down vertically in front of this. At some point, you're going to pull that door up, and the concrete is going to flow fairly quickly, and a measure of how fast that concrete, or the height that that concrete gets to on the other side, gives you a measure of how self-compacting that concrete is. So this gives you a little bit of passability. Some of the things that people worry about are the aggregates getting caught up on the reinforcing bars here, or having weird turbulence as they go through the reinforcing bars and not consolidating properly. Here's a picture of it, full scale, real life. You can see that this is the trap door right here that would be down when the test starts. You can see that as soon as this is picked up, the concrete is going to slosh out fairly quickly, and for a really good self-consolidating mix, you'll notice that it's a relatively uniform depth all the way along the L-box. Other versions of this exist. Obviously, if you don't like the letter L, U is a much better letter, and the basic idea here is to find out if the concrete is self-filling. You would again start out with concrete on one side of the chamber. You would lift the gate up that's in the middle and see how high the concrete comes up on the other side. And this is something that you would like if you want concrete that's going to fill in under a lot of blockouts or things like that in concrete construction. Here you can see more of a high workable concrete, but not necessarily self-filling. Doesn't really come back up the other side, where the self-filling is really going to come back up so that it's much more of a uniform height on both sides. Here it's a little bit tricky to see because the concrete leaves a little bit of residue on the surface, but you want something that comes up to be relatively proportional to on both sides of the U-box. Now, a few things that I'll point out here. This is an area that is rapidly emerging. If you would have asked people in 2000 or 1999 about self-consolidating concrete in the U.S., people would have looked at you, they would have scratched their head. It was pretty much something that was unknown. Well, it's been around since the late 1980s. A lot of that early work was in Japan. And due to language barrier and distance and other issues in the industry, it really didn't make it to other parts of the world. Toward the end of the 90s, it started showing up in a lot of the European countries, especially the far north European countries. I'm not sure what the appropriate term is, but the Viking types of countries Norway, Sweden, Denmark, Finland. You'll see a lot of self-consolidating concrete showing up there. In the 2002-2003, it starts to invade the U.S. market. SCC 2005 is a big meeting that was held in Chicago. SCC 2008 will be held, I believe it's November 2008, again in Chicago. This is something that the Center for Advanced Cement-Based Materials is doing, which Purdue is definitely a part of. And this is really the state-of-the-art of what's going on in this field. While a lot of these ideas have been placed into practice, there's still a lot going on making the materials more economic. There's also a lot going on into improving the quality control and the robustness of these materials. One of the real tricks with these materials, much like when we start to talk about high-performance concrete, the tighter you make the mix, and when we say here you're really reducing the margin for error, you're getting very close to having a little bit too much water, changes it completely. A little bit too little water changes it completely. So there's a lot of effort going on into making these materials more robust. Lots of efforts have gone into the precast and pre-stressed industries. Again, we talked a little bit about why they're producing one product. Here you can see them producing T-sections. Here you can see something that I've always found fascinating about self-consolidating concrete. There's a claim that it's going to reduce labor, but there's 1, 2, 3, 4, 5. There's always like 300 people standing in the background. I think it reduces labor once the audience goes away. And we can go a little bit faster. It can increase speed. There's some cost savings that can be associated with this, especially if you're recouping on both the materials and labor side. Less disruption to the public, especially if there's going to be a lot of vibration used or a lot of that type of information you could actually be casting at night, avoiding traffic jams, things like that. Also, as mentioned, there are some issues that need to be overcome. There are some benefits that you can get because you've eliminated vibration, and getting uniform vibration on site is a really tricky thing to do. Here's an example of a bridge made out of SCC. You're seeing this used more and more on a daily basis in the U.S. Experience in Europe and Japan shows that SCC needs more care than conventional concrete. This is simply because you're optimizing a mix, and as you optimize it, the margin for error gets smaller. Most of the common ingredients are going to be used. The big things that you're going to see that are different are you're going to see viscosity modifiers added, and the other thing that you need to keep real close track of, you need to really keep track of the volume fraction of the aggregates in the system, or the volume fraction of the paste. It becomes very easy to get a system that's paste rich to make the whole system move. It loses its economics when that starts to happen, and it loses out on some of its shrinkage capacity and things like that. It starts shrinking more. The robustness of the systems are being improved. Obviously, as you start adding more and more additives to the material, as you start adding more chemical and mineral additives, the system becomes more sensitive to temperature. One area where this is incredibly important is the idea of curing. You want to make sure that you get curing on it as soon as possible. The other area where there's a lot of practical interest right now is on formwork pressures. You've got something that's acting a lot like water when it's going into the forms, and in normal concrete construction, the cast rates or the pour rates are slow enough where you can dissipate some of that energy that's pushing out on the formwork. There's still a lot of work going on how formwork needs to be designed with SCC. There's a lot of debate on this right now. The formwork is currently, I believe, at least the last that I had heard, ACI is still recommending that it be designed to accommodate full hydrostatic pressure, which would basically be designing your forms to hold water. The big issue here is that this becomes expensive to do. So there's actually 2 very large studies going on looking at this right now. Training. Obviously, people need to be trained to do this properly. They need to be trained what to look for, and it will take people a little bit of time before they're familiar with this. There's also a lot of new tests that are coming out that are being used that give people a little bit better idea of the types of materials that they're working with. Questions on SCC before we jump forward into curing. Okay, so we'll start the discussion of curing. One of the things that we are pretty much on time as far as keeping track of where we are in the overall semester. We may even be about half of a lecture ahead. So if things are going by quickly, please wave, send an email, do whatever it takes to slow the lecture down. Basically, we want to talk a little bit about why curing is important. I'm going to talk about the big three aspects of curing. We'll talk about some different methods of curing and then talk a little bit about temperature and some different options. One of the things that I always find a little bit fascinating when we start to talk about concrete is you can look at concrete and how the world views the materials that you're dealing with. I always find it interesting if you watch, for example, you watch one of the news programs at night. They'll have a big expose on concrete, whether it's a murder trial and they're trying to figure out if the concrete in the bottom of the boat is the same as the concrete that they had in their driveway, is the same as the concrete that they found with somebody, or if they're talking about a structural failure or something like that. They'll always have a problem identifying and understanding cement and concrete and the differences between them, and they'll go through these very complicated discussions of what cement and what concrete are. But it seems like a lot of other materials, they'll just throw out the phrase space-age polymer or space-age composite, and it sort of just stays at that point. One of the things that I find a little bit interesting is if we look at the materials that the public sees civil engineers using, they typically will take on their own connotation. And here we can see the dog who obviously had a problem with the underworld. He bit the Godfather. We can see that Larson has chosen to show us that this is concrete. And one of the things that Larson always does to let you know when he's drawing concrete is he puts a nice crack into the concrete as well, so that you know that the concrete is cracked and it wasn't cured properly. So my mission over the next 35 years that I'm at Purdue is to try to make it so that Gary Larson can draw concrete without cracks and the public would accept that that's uncracked concrete that's being used. So we've got a long way to go, but I think we can get there. Curing, a few of the questions or reasons why we might be interested in this. Concrete must be cured properly to develop the optimum properties, and there are several different optimum properties that we may be talking about. We've actually got one picture that's missing here. I don't know why it's elected not to jump up onto the screen today. Basic idea here is there are two things we're going to be after. One is primarily associated with the removal of formwork. So a lot of the reason why there's a lot of interest in how concrete cures, how concrete gains strength, is because it's directly related to how fast construction operations take place. And if you've ever heard the expression time is money, nowhere is that more true than on a construction site. The idea of being able to open a road very quickly to traffic can mean hundreds of thousands of dollars a day to a particular contractor. There are penalties, there are incentives for them opening roads to traffic. If they can understand curing a little bit better, they can understand methods to predict how fast the concrete is gaining strength, they can be in pretty good shape. The other thing, and I'll draw it here since I'll use all of my artistic skills. There's a picture of a beam here. And one of the other things that we will come in contact with quite frequently is that the properties of the concrete are directly related to how that concrete was cured. And one of the reasons that this is a big deal is because you're looking at acceptance of materials typically being related to a concrete cylinder that was cast alongside of the road. It blew over, it rolled around, it got baked in the sun and wasn't cured properly. And you're expecting that particular cylinder to represent 40 or 60 or 100 trucks of concrete that was replaced that day. And I think one of the things that the concrete community doesn't take enough interest on is really looking into making sure that the samples that they're taking to be quote-unquote representative of the concrete that's in the structure, making sure that they're actually cured in a very similar way to making sure that that happens. Now, here is a picture of the Hall of Shame of some different concrete structures. I will point out that some of these are actually in Lafayette themselves. You could see this one up to a few years ago if you happen to drive across the Wabash River. You would have noticed this because your car would have jumped up and down about every 12 inches where the reinforcing steel was placed. One of the things that you can notice is that you can now conveniently find all of the reinforcing steel at the bottom of these divots. Here you can see again cracks where you've got rust streaming out of those cracks. The rust is basically just coming down the side of the column. Here, the cover that was on the bottom of the reinforced concrete to protect the steel from the environment has obviously outlived its life on that bridge and has decided to either fall off onto the cars below or has decided to fall into the river below. But either way, it's not doing what it was intended to be doing there, which is to provide bond to the reinforcing steel and to be protecting it. And here you can see some of these sidewalls, again, other aspects of this type of problem. Now, I will point out that a lot of people, when you talk about curing, they talk mainly about moisture curing. They want to make sure that concrete stays nice and wet. What I'm going to talk about here is that curing is really the combination of three things, and if you don't have any one of these three things, you're going to have a problem. Curing is related first to time. Time is sort of the ultimate equalizer here. We're talking about how long the concrete is at a particular temperature, how long it's underwater, how long it's been since it's cast. So time is one of the crucial components when we start to talk about curing. Temperature, component number two. We saw earlier that the temperature is directly related to how fast the cement is going to react inside of the system. We also saw that this could be related to the structure that starts developing in the system, so temperature is going to be another important component. And the third component of all this is moisture. If any one of these is missing, the other components aren't going to be able to be doing their effect. So you can have a system that's got plenty of temperature, plenty of moisture, but if you don't allow it proper time, it's not going to be able to develop its strength. Similarly, if you keep something at 0 degrees, give it lots of time, lots of moisture, it may not be developing the types of strengths that you're after. Now, one of the things that I will point out here is that you need to be prepared to fight for your curing. Very few of us in the room will be able to take on the gloves and knock out an inspector on the field, or knock out an inspector out in the field, or knock out the contractor in the field to make sure you get your curing. But this is one of those areas where you need to really be able to sort of stand your ground and say, we want the concrete cured properly. If you don't cure the concrete properly, you're not going to get the properties that you're after. You're not going to get the properties that the system is designed based on. And the problem with most curing is if it doesn't show up with early age cracking, it takes 10 to 12 years to show up. And this means that you could be improperly curing concrete for 10 or 12 years, reducing the long-term value of the concrete, and this is something that's relatively easy to do. The big reason that curing is such a problem in the U.S. is it's not a direct cost line in most contracts. Most of the time this is just a requirement of the contractor, so the contractor will cure the concrete properly for 3 days. And it says something like that. Properly becomes a very vague term. The idea that if they're not getting paid, it's like any of us, if I said, oh yeah, do lots of homework, but I'm not going to grade it, I'm not going to collect it, I dare say there'd be a few of you who would push the issue and try not to do that homework. Same thing with curing. Now you'll notice that there are some Canadian groups who actually pay for curing, and they get concrete that is much better cured because they actually have a separate pay item that pays them to put water up on the surface of the concrete. So again, the basic idea here is if the concrete starts to dry out too early, if it's in air the entire time versus being moist cured, you will notice that the strength will decrease after a certain period of time. It won't be able to gain the strength that we would have. Now, everything that I say that's related to strength is even more critical when we start to talk about durability properties, when we start to talk about moisture absorption, when we start to talk about ion transport, even more important. Compressive strength, again, is going to be related to the temperature that the concrete is maintained at. At some long-term time, all of these are going to reach the same value. But at least in the immediate term, it's going to take a lot longer for concrete that's at 33 degrees Fahrenheit to gain the same strength as 70 degrees. Remember, we had the rule of thumb, 18 degrees Fahrenheit is about half the rate of reaction. So if you want to double the rate of reaction, you take concrete from 70, start cooking it at 90 degrees, you're about doubling the rate of reaction. Now, there are a few places where I think there's a little bit of a misconception on what we mean by different types of curing. So what I'm going to do is try to walk through the different types of curing and talk a little bit about some of these. We all know that water is a vital component of the hydration reaction. We couldn't write any of the equations that we wrote earlier in the semester with the C3S or the C2S reacting without having water present. The basic idea here was something that we were talking about last time. The real reason we want to control the water to cement ratio, the real reason we want to control the water that's inside of the mixture is to lock the porosity into a particular form. So the reason we spend so much time talking about the water to cement ratio and don't add water and all that is to make sure that the porosity gets locked in with a specific structure, porosity that are related to a particular water to cement ratio. We go back to Powers models. We could see that the water to cement ratio was directly related to the permeability of the system, directly related to the strength of the system, directly related to the pore space in the system. That holds until the concrete goes from a liquid to a solid. Once the concrete becomes a solid, the structure of that paste is more or less fixed. At a large scale, it's really kind of fixed. And from that point on, the only thing that water is going to be doing is it's going to be helping the reaction process. So before set, you want to really control the water content because it's going to dictate the water to cement ratio. After set, however, add all the water you want. Right? The water that's added is going to help the hydration reaction. So occasionally you'll see things that may look a little bit odd. Here you can see what I think is supposed to be misting. This is a fairly substantial mist down here at the nozzle, but the basic idea is that you are creating an environment that's over top of the bridge deck that's being cast here that has a relatively high humidity, and because of that you're not going to be drying the water out of the concrete as rapidly. On the bottom you can see somebody here trying to make their concrete grow. They're using a typical sprinkler system. Sometimes you'll see soaker hose across the top of the concrete surface. Basic idea here is to create a water reservoir from some external source, and this water reservoir is going to protect the surface of the concrete. If water is evaporating from this water reservoir, it won't be leaving the system. Water is going to be happy to be staying inside of the concrete system because all of the water is coming off of this water that's on the outside surface of the concrete. The additional benefit is some of this water will actually get sucked into the system. We talked about the fact that when the system sets, when all of a sudden when you get that structure formation right around the time of set, the chemical shrinkage is going to continue to increase, but the volume of the system is relatively stable. So what it's going to do is it's going to try to reabsorb bleed water. It's going to try to suck water in from the outside edge. And if you took a cylinder and you placed it into water right around the time of set, you could come back and notice that that cylinder has gained weight. The reason it's gaining weight is it's trying to suck water in from the outside to fill up the empty pores that are being created by chemical shrinkage. So water ponding is the real way where you're going to get water back into the system. Now you may ask the question, is this a problem? It's not a real problem because you've got the structure locked in place and all you're doing is filling in that chemical shrinkage. All you're doing is filling in those vapor-filled spaces that have been created while the system continues to hydrate. The more water in the system, the more it's going to hydrate. So you're in pretty good shape if you're using water curing. Now, one of the other aspects of this that we need to think about, and this is some data that was taken from Powers' work from the 1940s. This is a measure of the amount of water that's taken up. So amount of water is on our y-axis. Our x-axis is the relative vapor pressure. Amongst friends, we could call this the relative humidity. All right, so if there was a physical chemist in the room who wanted to fight, we could fight for an hour, and believe it or not, I've actually had that fight in a class that's very similar to this about the differences between relative vapor pressure and relative humidity. I'd be happy to discuss that with anybody in greater detail if they'd like to come for a knockdown, drag-out battle in my office later on this afternoon. But amongst friends, we're relatively close to calling this the relative humidity, at least for this example. The basic idea here is Powers took some powders. took some cement powder and he kept them in 100% humidity, 80% humidity, all the way down to 0% humidity. Very dry system. All right. The idea here is what he measured was he measured how much water would be taken up by that powder to be participating in the reaction. And not surprisingly, what you can start to see is you can start to see that the amount of water that's absorbed by these different powders depends upon the relative humidity that the powder was exposed to. The higher the relative humidity, 100% relative humidity, you see a lot of water is taken up by the system. Some of this water may or may not react, but a lot of this water has reacted. So this tells us that if we want the entire concrete system to be reacting, we want the cement to be hydrating, we need to have a relatively high relative humidity. Right? We need to keep this relative humidity high. Now in concrete, we're not going to get up to 100%. There are salts in the pore solution which cause this to cause us to have to look at these ideas of relative vapor pressure. We can bring in Raoult's law and things like that. But the basic idea is if we are above about 96, 97, 98% relative humidity, we have a system that's nearly saturated. There's enough water in there to be participating in the reaction, and we're going to get the most reaction that's taking place in that cement. As you drop the relative humidity, water is going to start leaving the system. As more and more water leaves the system, the cement is going to start hydrating less and less. And once you drop below about 75 or 80%, there is a marked decrease in how much of the reaction is taking place in this particular system. Once you get below about 40%, you just have layers of water inside of the overall pore structure, and that water is not going to react. It's just going to hang out on those surfaces. So really the crucial point, and what a lot of people sort of use as sort of the rule of thumb, below about 75%, 80% relative humidity, they assume the hydration reaction stops. Now is this 75 or 80% ambient humidity? No. It's inside of the concrete, inside of the pores of the concrete. So if you were to maintain a concrete at 40% relative humidity, eventually over time the concrete would get to that point. Where is this going to be the most severe? Well, which parts of the concrete are going to dry out the quickest? I dare say if anybody walked out, and again, I can't tell you that it's cold outside today, but imagine a day where it's cold outside. If you walked outside and it was cold, which part of your skin would get, or which part of your body would get coldest the fastest? The surface, the outside part. So temperature changes are going to be the most dramatic at the surface. Humidity changes are going to be most dramatic at the surface. So the big problem here is you may get a surface that comes to 60 or 70% relative humidity fairly quickly and stops reacting. The core of the concrete continues to react, so when you measure a cylinder, you don't see a big difference in the overall strength because the majority of the cylinder is the core of the cylinder. But if you start to look at ions going into that concrete, salt getting sucked into the system, the diffusion into the system, that surface concrete, conveniently called cover concrete by a lot of people in the business, that's going to be much more porous than the core part of the concrete and allow many more things to come into the overall system. After you've gotten the system to solidify, add all the water you want. Some of the ways that you could do this, cotton mats. Ponding can be difficult to do for many applications. If you've got elevation on a concrete surface, if you've got a surface that's vibrating, you've got a surface where it's difficult to pond water, it may be a little bit difficult. So one of the things that people will be doing, they'll be using cotton mats, burlap, rugs, old carpet mats get used. One of the things that I will point out here, if you're using any sort of a recycled material like the underlayment of a carpet or something, if your dog puddles, left puddles on the carpet, it's highly likely that when you add water to that carpet underlayment, whatever puddles left behind is going to stain the surface of the concrete. So you want to be real careful if you're using some sort of a recycled material to make sure you're not discoloring the surface of the concrete. The color of these mats may be incredibly important. White is the color you'll want to use in the summer to try to reflect some of the heat. You'll see places where they're trying to extend the construction season where they may be actually using a dark color to try to absorb as much of the solar energy as possible. One other thing that I will point out here that's incredibly important from a practical point of view in a litigious society, you do not want one of these cotton mats blowing all over Interstate 65. All right? If your car drives into a great big blanket and the driver can't see anymore, it is a big safety issue. So you got to make sure that these mats are properly secured. Fogging, another case that you'll see people doing quite a bit. The idea here is to change the humidity. So you'll have a different relative humidity over the surface of the concrete. It will slow the evaporation rate, minimize evaporation. Sometimes you'll see this done with these fogging hoses. Other times you'll see people doing lawn sprinklers or soaker hoses, things like that. Now, a little bit different technology. We're not going to be adding water in this particular technology, but the application of a curing compound. Here the basic idea is you're going to cover the surface of the concrete with a wax or resin or a chlorinated rubber. The basic idea here is that this is going to seal, or at least partially seal off the surface of the concrete. So unlike the other case where you saw us adding water onto the surface of the concrete that could be absorbed or could provide its own evaporation, in this particular case, what we're doing is we're essentially putting a film of either wax or some sort of resin over the top surface. Now, the idea here is that this film is going to slow down the evaporation from the concrete. In the best possible case, it would prevent it. Right? But that's not necessarily what we're always going to have. It's really going to slow down the system, slow down evaporation. It's not going to add water back into the system. The other thing I'll point out is many times in these curing compounds, the real value of this depends upon how uniformly that curing compound was applied to the surface of the concrete. So usually there's a color that's added to the wax or added to the chlorinated rubber. The color is generally white to help keep the concrete cool and to allow you to see where the concrete was sprayed. Many times this is put on in some sort of a controlled fashion. So here you can see them spraying it on the surface. They use application rates that are basically gallons per square foot or gallons per square meter. Uniformity is the key. I was out on one site, and one way that this will be done, especially for small residential, light commercial type applications, is they'll put it in something like a garden sprayer, and they'll spray it out across the surface of the concrete. And we'd come back a year later, and one of the things that the owner had noticed is that the concrete had a very funny pattern where it looked like it was peeling off. And you could see that John really loved Mary a whole lot because he was writing this with the garden sprayer when you got above the surface, because he had great curing compound coverage in certain spots where he was spelling this out, and in other spots he had sort of missed those points. One thing I would remind you of doing, it's not usually the president of the company that's out there spraying the curing compound on, so you want to make sure that you're really making sure that everybody gets a uniform distribution of that curing compound across the top surface, and this is really what we want to make sure. Don't be cheap when it comes to applying the curing compound. It's not that expensive. This is the water that's lost through a curing compound for different application rates. One of the things you'll notice is once you get up to the recommended dosage rate, you'll see that it's cut down considerably and can be a very beneficial application to the surface of the concrete. Plastic sheeting, again, creating a film, preventing the evaporation, or at least minimizing the evaporation coming up from the surface of the concrete. Here you can see that there's a dark plastic being used to try to heat up the concrete underneath. The main thing I would point out to you here, you can see there's lots of debris thrown across the top surface of this plastic sheet to try to keep it down on the surface of the bridge. You will notice that depending upon where you're at, you can get some pretty windy conditions that all of a sudden pop up, and you do not want to be dealing with the fact that 30 cars got covered with a sheet of plastic that you covered the bridge deck with. It can be a major issue, so you want to make sure that that's taken care of. Interrupted curing, if for some reason the concrete surface dries out, add more water. All right, it'll kick up where it started. Freezing may cause a little bit of a problem, but we'll talk a little bit about that later. Night placement, concrete always looks better at night. Here you can see them doing night placement. There are two main reasons that they wanted to do night placement in this particular application. One is it's going to reduce the temperature of the system so that you're not being stuck with real hot temperatures at the end of the day that are basically being added to by the heat of hydration inside of the concrete. The other thing is the winds in this particular location will typically die down at night so that you get a lot better concrete when it's placed at night, because as soon as the concrete's starting to hit its peak temperature, it's about 4 or 5 o'clock in the morning when the temperature that's around is a little bit low, so it makes the thermal cycling a little bit better, also minimizes the evaporation that's taking place at very early times. What can happen if you don't cure properly? Well, you get a concrete surface that looks like this, where you can see a lot of these cracks that are forming. They're relatively parallel to one another. They're relatively random in general orientation, although in this particular case you can see they sort of line up, and we would guess that the wind is going in this direction and there's reinforcing steel going in this particular direction. This is pretty typical of what we see as plastic shrinkage or plastic settlement cracking. This is cracking that typically is going to occur during the first 24 hours. And I will tell you that while this may not be a huge structural issue, it is a huge issue if you have an owner who is actually going to go out and look at the surface of their concrete. With the type of work that my father does, he has a lot of people who will actually walk across the surfaces of the concrete. This is one of the things that he does not want to hear about on Sunday when he's playing golf. He does not want somebody out there looking at the surface of the concrete and noticing these plastic shrinkage cracks, because there's very little that can be done with it after these cracks are there. Once these cracks are in, it's very difficult to get rid of them. The basic idea here, there are a few things that we can actually be looking at so that they don't happen. There are a lot of things that can cause cracking, especially in fresh concrete. And what we've done here is we've broken this up into two different types. We've got cracks that form before the concrete hardens, generally during the first 24 hours, and then cracks that form after hardening. Before hardening, we see things that we've already talked about: formwork movement. All of a sudden, a few hours in, the formwork starts to move. It settles a little bit. You can see a subsidence crack. Subgrade movement, we talked a little bit about that. What we're talking about right now is this idea of plastic shrinkage and plastic settlement. High strength, low water to cement ratio concretes, autogenous shrinkage is becoming more and more of an issue. We'll talk about this, really important for low water to cement ratio concretes. And then things that we could see from freeze thaw or frost damage. One of the best quotes that I ever heard was out on a job site looking at concrete for a particular ready-mix producer, and he said it was obviously not his issue. When they supplied the concrete, when it came down the chute, there were no cracks in it. He didn't add any to the back of the truck, so it was obviously somebody else's problem. While that's a great idea, or that's a great concept to try to propagate, and I encourage you, if you're a ready-mix producer, to try that as many times as you can, it's not going to work very many times. There are about 20 or 25 things that can lead to early age cracking, and you really want to make sure that you try to take care of each one of these really to the best of your ability. Subgrade movement, we talked a little bit about this idea of subsidence. Really important in construction, really important when we start to talk about frozen soils. We really don't want the concrete to all of a sudden sink and then we get some sort of cracking above the surface of the concrete. Again, formwork movement, you can have a concrete that's starting to set up. All of a sudden the forms bow out a little bit and you develop a crack across the surface of the concrete. Can be a big issue. Plastic cracking is going to occur on the surface of the fresh concrete. Generally, you're going to see these spaced apart 12 inches up to a meter. They're rarely going to extend all the way across the surface. They're going to be relatively irregular. They do not generally impair the strength substantially, but they are incredibly unsightly, and most of the time you're going to see that these are related to one of three areas. They're either going to be related to settlement, evaporation, or autogenous effects. And I would tell you the one that gets the biggest amount of play is evaporation. Everybody knows about evaporation. Very few people know about these other two. So we'll try to make this sort of a balanced discussion and keep all of these all of these in discussion. Now, I threw this image up at one point. This is an image that I've taken from the Japanese Concrete Institute, and I believe it also came out of the British Concrete Institute. And I put this up for a contractors meeting once, and there were a bunch of them snickering, and I had to ask the question, and a couple of them were proud that they've never had a structure that looked like this. I will say that that's something to be proud of, but this is an illustration showing about all the possible types of cracking that you could have in a particular structure. Plastic settlement cracking, the basic idea here, if we look at this cross-section that I've got in the upper portion of the upper, I guess, left-hand portion, this is a cross-section. The dark spot here is a reinforcing bar. This box that should be colored in a particular color, this is the concrete inside of the system. And as I mentioned, as the concrete is starting to set before it solidifies, the cement and the aggregates are going to try to sink. The water is going to be trying to migrate up toward the top surface. Now, if the entire system was uniform, this wouldn't be a big issue. If this was a large box of concrete, it wouldn't be a big issue. The big issue here is the fact that you've got a reinforcing bar. So what's going to happen is the concrete on the one side of the reinforcing bar is going to settle 2 or 3 millimeters. Over the reinforcing bar, it just can't settle that much. So you're going to get this weird displacement pattern taking place across the top surface of the concrete. What's going to happen is you're going to start to see these small fractures forming over top of that reinforcing steel because it just can't extend that much. So plastic settlement cracking is going to occur over reinforcement. You'll also see this here where you have a change in the depth of a section, or where you're changing the height of a section of concrete. Same idea. The concrete is going to settle differently. Sometimes you'll see this in real deep sections where you see a lot of settlement. The basic problem here is if you've got a very, very low or very, very high slump mixture, you can see this. It's got low stiffness. It's drying early. The big solution to this, if you see this happening, re-vibrate the concrete. All right, get in there. It's usually early enough where you can hit it again with vibration, and you can just basically get this out of the overall system. So here you can see it in a deep section in a column. Here you can see it right over top of the reinforcing bars. Here you can see it where you've got a change in height. Here's some testing that we had done a few years ago to try to look at this. As I mentioned, what you're going to see is it's going to be generally lowest between the reinforcing bars. It's going to come up to the height above the bars, and then you're going to get a spot here where the crack can actually start. It's going to start at the top, and it's going to start at the top of the bar, and these two cracks are going to try to get toward one another. The basic thing is you're causing a tensile stress to start developing over top of the surface of the reinforcing bar. So one of the things that we tried to do is we tried to measure this with a non-contact laser. Again, remember you've got concrete that's settling, it's bleeding, so it's a little bit more complicated process. If the surface was going to stay where it's supposed to be, it would stay right at that red line that I've just drawn. Because of heat in the system, it's going to expand a little, and then you're going to see the concrete start to settle. The concrete is going to settle, and at some point, that settlement is basically going to be gone. And that point where that settlement is really gone is either where the system is completely consolidated or where the system has set. While this is settling, this is synonymous with the idea that bleed water is coming to the surface. The surface is moving down. We're measuring that as a settlement. Water is moving up and coating the top surface of the concrete. Now, a little bit of this is not a problem. A little bit of this is expected. That water that's coating the surface is actually protecting the surface. All right? It's exactly the same thing that happens when you sweat. Bleeding is concrete sweating. It's basically forming a protective layer of water across the surface that's going to preferentially evaporate. One of the things we tried to point out here is that you can get this expansion. This occurs mainly because of how quickly it's being placed. The other thing that I'll point out is that you'll see the greatest expansions in sort of concretes with sort of mid-range workabilities. If it's really, really soupy, it tends to flow and you don't have a consolidation problem. If it's really, really stiff, you don't have a consolidation problem. Somewhere in the middle is where you get the biggest movement. Here's a picture of the system that's measuring it. I've drawn these red lines in for your edification. They are not the actual laser beam that is happening. But the basic idea is the laser is going to shoot down toward the surface. It's going to bounce back up and it's going to be captured here on something that looks a lot like a digital camera. It's going to be a ceramic metal oxide semiconductor. Depending upon which one of these fins of the CMOS that actually activates, it tells you how far you are away from the surface. Since you started out with this fix, the surface is moving, it will tell you that the concrete is settling as a function of time. Here you can see the effects. We've got a plain concrete. We've got a fibrillated concrete with fibrillated polypropylene fibers. One of the things that the fibers do is they make it a little bit more difficult for the concrete to settle. This is one of the reasons why the fibers tend to work. They tend to help with plastic shrinkage cracking. They really help on the settlement side. The second component of this is really the component that really gets the most discussion, and this is the evaporative component of it. It's going to occur over reinforcement. It's random locations on diagonals depending upon the orientation of the wind. It's going to occur very, very early on. The solution is really to either improve curing or use fibrillated polypropylene fibers or cellulose fibers, any type of fibers that has a very, very high surface area. High surface area per mixture. You don't need a lot of these fibers. They tend to be very low volume concentrations, but they tend to have a lot of surface area. And it's mainly because the fibers are going to do one of two things. They're either going to help to reduce settlement or they're going to help to wick water up toward the top surface. So they're going to basically increase the bleeding rate of that particular concrete. Now, while this is going on, you've got your initial concrete that's been placed. You've got these, which are my cement particles that are basically sinking down. You've got the water, which is trying to work its way up to the surface. You don't get as much compaction at the surface because you just don't have as much weight or consolidation going on in the concrete. And if you had no evaporation, you would be creating this layer of bleed water that we've been talking about. In cases where you have evaporation, that is going away, and if the evaporation is significant enough, it's going to actually start to de-water the system, just like we would see with a gel or something like that. It's going to de-water the system, and it's going to start to cause the water to evaporate out of the pore space. And when you get the water out of the evaporation of the pore space, that's when you're going to start to see these big problems with the potential for plastic shrinkage cracking. So the basic idea here is bleeding is water that's being extruded out of the solid system. It's basically due to the difference in specific gravities of the material. Evaporation is taking place from the top surface. If the bleeding rate is greater than the evaporation rate, in general you don't have a big problem. However, if the other is the case, where the evaporation rate is greater, then you can have a problem depending upon when this happens. So if you start getting excessive evaporation taking place from the concrete surface, you can get this potential for the water to start to recede between these two particles. And when the water starts to recede between those particles, you start to build up a tension inside of the fluid. This is an equation that we're going to use quite a bit later on in the semester when we start to talk about shrinkage, we start to talk about volume change inside of the system. The basic issue here is you've got a surface tension being created inside of the fluid. Water doesn't simply just recede between those two pores. It actually recedes in a way where it starts to cause a meniscus to form. And this meniscus forms because you have an imbalance in the surface energy of the particles depending upon where they're at inside of the overall system. If it's down in the body of the system, it tends to have other particles around it that can balance that out. If it's up near the surface, it's going to start to form a meniscus because it wants to cling to the surface of the cement particles. And the big implication of this meniscus that's forming is it's going to be directly related to the amount of stress that's forming inside of the fluid, the under pressure that's forming in the fluid. So the stress that forms, sigma L, is going to be equal to 2 times the surface tension of the fluid at the liquid vapor interface divided by the radius. Now when we talk about this, we're here talking about the pore radius, we're talking about the distance between some of these particles. Now there's a lot of assumptions that go into this, there's a lot of approximations, but the basic thing that you can start to see here is that the stress that develops in the system is inversely proportional to the radius. So the smaller the cement, you're using silica fume, you're using really fine particles, that means you're going to have a smaller pore space in the system. Particles are going to be closer and closer together. That means that your capillary tension or your stress that's happening inside the system is going to be higher and higher. So that's one of the things that you can notice. Smaller pore spaces. Higher strength concretes are going to get higher capillary stresses developing inside of them. The other thing that I'll point out is that the surface tension is up here on the top, and what we're seeing is a lot of new additives, new admixtures coming out that are working predominantly on the surface tension of the fluid. The goal is to reduce the surface tension. By reducing the surface tension, they're reducing the capillary stress under the exact same type of condition. Big idea here, the big pores are going to empty first. The simple reason is because of an energetic concept. Energy is going to cause the big pores to empty out first. Once the big pores start to empty, we're going to start seeing smaller and smaller pores empty. Now, I will leave till Wednesday the discussion of the great ACI nomograph, which we see here, which will help us to determine things like the evaporation rate.